bit more chapter 4, and I think we'll get through that in half the lecture. And that gives us some time to ask questions and discuss things. And I put this new slide in. I think I might have put another new slide in, but anyway, just to get us slightly reviewing what we've been talking about, but giving a slightly different amount of information. And then we'll start chapter 5, I'm guessing. So what's shown in this slide is on the left, what I envision as a point source. It says size D, but it's a point source. And there are spherical waves going out, and they cover a certain angle theta. I didn't complete the diagram completely, but this angle theta is just measured up from the axis, so let's say up to the arrow here. Okay, at some wavelength lambda, which is measured between the peaks or the crests of the waves as the waves are propagating out. And what we discussed was there was both spatial and temporal coherence. Spatial coherence being in the transverse direction. So if the waves are propagating out to the right, what is the coherence? What's the expectation that you could predict the phase in one point if you knew it in any other point? Okay, and so if it's a point source and it satisfies this relationship, then you've got near ideal, or for a point source you have ideal conditions, ideal spatial coherence. And I showed you the front page from that book by Emil Wolf, this famous chapter 10. The thing I forgot to tell you, and why I pulled it up, was in that front page, he says, no physical source is completely coherent, okay? Because no physical source is really a point source, and it doesn't oscillate in and out of the board. It doesn't oscillate forever, so if it has a finite oscillation time, it has a finite bandwidth also, so there'll be a finite coherence length. So he just said, no physical source is completely coherent. All physical sources are partially coherent. I showed you, so this was a relationship for the coherence length in the propagation direction. I'll try to give this more meaning later, but if you have a comment now, or while this slide is up, please do it. And then spatial coherence, what's the condition if this is a point source? And we used the uncertainty principle to come up with a relationship. This is kind of a surprisingly easy way to come up with this relationship, and I'm going to show you the sophisticated way to do it today. Well, I won't show you, but I'll give you a slide or two on how it's done. But we had a relationship that D times theta, where those were RMS quantities. The D was twice sigma. But we had D dot theta equals lambda over 2 pi. And I mentioned that actually, if you do it in terms of full width at half max, where rather than D being 2 sigma, it's a full width at half max. So this is some distributed source, okay? And you have an angle, also Gaussian, both Gaussian, with a full width at half max for the full angle. If those two things are approximately equal lambda over 2, that's the same as the D dot theta equals lambda over 2 pi for Gaussians, and you'll have a essentially full spatial coherence. Okay, so this is spatial coherence, this is temporal coherence. What happens if your source is a little bit bigger? It's not a point source like it was before. It's twice as big or 3 times as big or much larger than that. So I just modified the drawing here, and I took this relationship, which by the way is in blue here on purpose, and I put it here where the product of the size and the angle of radiation, again full width at half max, it's larger than lambda over 2. So approximately equal to lambda over 2 got your full spatial coherence. What happens if it's larger? And what I made a little diagram here, again, playing with this blue color. Within a smaller angle, it would be lambda over 2. It would be full spatial coherence. So if D were, for instance, twice as big, if this D was twice as big as the other, then the angle over which you'd have full spatial coherence would be half as big. If this is 10 times as big, then the angle over which you've got spatial coherence is 10 times smaller. And outside that area of relatively good coherence, the wavefront just starts to flop apart, okay? The variability of the phase fronts starts to vary and they mix with each other. And so I was hoping this might help to give a somewhat clearer picture of what we mean by spatial and temporal coherence. So any comments or feedback on that?
Professor, sorry,
Yeah.
could you go over the point where you said if lambda is 10 times bigger than something else is
Oh,
10
no,
times
no, yeah, it
smaller?
wasn't
Or
lambda.
sorry, yeah, I mixed.
That's okay. No, good. Thanks for the question. So here I've said in this case on the right that the product, the full width half max products of these two quantities, d and 2 theta, is bigger than lambda over 2. I didn't say how big, but then I said as an example, if this product was twice as big, for instance, the diameter was twice as big, then for coherence, for this condition on the left to hold, if d got twice as big, this would only hold over half the angle. So if I wind up with a source that's twice as big, I can expect that I'm only going to have good coherence over this smaller area. So, so sometimes you live with that because your source subtends an angle that's only half as big. Okay.
Great, thank you so much.
So some experiments that require spatial coherence. So I'm going to give you a few examples here. They're going to come up again in the next chapter, but X-ray standing waves, which can be used, for example, for depth profiling or probing of materials properties. So I'll show you where you have X-rays incident and reflecting off a surface, and they interfere, and they produce a standing wave pattern with maximum and minimum. Go over it in a second. And that you can only get standing waves if you have some degree of spatial coherence. How much? Well, you plan that for your experiment. Also, so-called STIXM microscopes, a scanning transmission X-ray microscope. The ALS, for example, has a really excellent quality STIXM, and that requires spatial coherence. So I'll show you in a little while why that is, but that microscope requires spatial coherence. We have other X-ray microscopes at the ALS, so-called full field microscopes, which don't require this coherence at all. So there's big advantages to both, actually. And when we get to imaging, we'll go over it more, but if you're interested, just ask a question now when I have a diagram in just a few minutes. There are two kinds of other versions of imaging. One, coherent diffractive imaging. It's called CDI, where there's no lenses involved, but it requires a coherent illumination of your object, and then that coherent light scatters off the object and you collect it. And there's a procedure of reconstructing from the diffraction pattern what the object looked like. So that's called coherent diffractive imaging. There's another thing called tychographic nanoscale imaging, and we'll talk about that when we get there also. And then there's X-ray holography. So as in holography for visible light, X-ray holography has been done, providing nanoscale imaging, and people still do it. And in fact, I saw about 2 years ago, a young scientist at SLAC used the free electron laser there, much like our undulator radiation, but more powerful, and to do nanoscale holographic imaging. Is really quite a great thesis topic, I believe. So here's the standing wave pattern. So if your radiation is coming in and it's spatially coherent across this wavefront, and it reflects off the surface to some degree, if it's spatially coherent, there's going to be an interference pattern. Again, as long as the spectral bandwidth is narrow enough to provide enough of these interference planes. So this is a diagram. It's our usual formulas for spatial coherence and temporal coherence. And the planes here, they satisfy this relationship. And if you pull this, if you make the angle smaller or larger, these planes, this is the dark planes, by the way, the dark lines mark the maximum of the standing wave interference pattern. In other words, the incident light electric field and the outgoing reflected light are interfering with each other, and they cancel in most places, but they interfere constructively. And there's a sort of sinusoidal pattern here going vertically up, but the location, the phase of these things from the surface, or their location above the surface, depends on all of the parameters, but presuming you kept lambda fixed. As you change the incident angle here, the pattern moves up and down, okay? And the pattern will have a separation that's shown here, okay? So lambda over 2 sine theta. So I know this was developed at Cornell many years ago, but for instance, I know a young guy who did his PhD thesis just a few years ago at the synchrotron Indus 2 in India, which does not have good coherence properties. But he did enough spatial and spectral filtering and still had enough signal that he could do this, and his PhD thesis was to observe the fluorescent emission in some thin layer that was covering this substrate. So there's a thin layer. I don't think the curve that's shown here, I think, yeah, this is from Cornell University, now at Northwestern. But in this example, not the one from India, but the first one to do it, there was a layer here of zinc, and or as a multi-layer coatings, okay, and deposited. And what happens is the light would come in, go out, interfere, and at these maximum areas, the intensity is high, and those atoms could be excited, and then by knocking out a K shell, in this example shown on the bottom, and then as with the K shell vacancy, when an electron dropped in from n equals 2 to n equals 1, you get the characteristic K alpha radiation, which for zinc is shown as 8.64, and you see the fluorescent emission that way. And as you move the pattern up and down, these patterns move left and right. So this is the angle that they're varying, but this is actually going to be height above the surface, which you can just get from the geometry. So that's an example that requires coherence, spatial and temporal coherence. Here's our STIXM. So as it says at the top, scanning transmission X-ray microscope. So basically almost all the microscopes, X-ray microscopes, are transmission microscopes. The X-rays go through, they're partially absorbed, and you want to image where they're absorbed and where they're not absorbed to find out what elements are there. A simplified diagram, if you're interested, look in chapter 10. You'll find more complete diagrams, but here's an undulator. There's a monochromator. For instance, for soft X-rays like at the ALS, this would be a grating monochromator that rotates, and therefore the apparent line spacing changes, and the radiation is diffracted up, depending on the angle again, and depending on the grating spacing. And that goes up. So that's allowing you to choose what wavelength are you looking at in your microscope, and you want to see how that light is absorbed. Excuse me. So the radiation now has been spectrally filtered, in this case to get a specific wavelength of interest. So you're interested in cobalt and some magnetic material. You want to tune this with the exit slit and everything to just pass an energy that's good for absorption in cobalt. So let's say the cobalt maybe K alpha or something. Then you put a pinhole. The pinhole generates spherical waves, and then there's a lens, a zone plate lens, which we heard a little bit about, but it has many of the basic properties of a lens. Zone plate lens does. It's not it's not highly efficient. That's its downside, but it can get you a very high resolution. And just imagine it as a lens. Don't try and understand everything about the zone plate at this moment. This lens is focusing this radiation with spherical wavefronts down to a small area. And in fact, that's the trick. The lens is actually imaging the aperture, pinhole aperture, onto the sample. So this is a lens, has a focal length, and for this relationship, maybe this is the object distance and this is the image distance, and 1 over p plus 1 over q equals 1 over the focal length. Okay, so in this case, the focal length depends on the wavelength. That's one of the properties of a zone plate. But let's say we have a fixed wavelength, and this is now imaging the aperture onto the sample. And the reason for the spatial coherence is that a pinhole with the spherical wavefronts can be focused to the smallest spot size. So this is imaging the aperture onto the sample. If the aperture is big, not producing diffraction limited wavefronts, the wavefronts are a little more jiggly and the spot size will be bigger. So, and it's just proportional. This lens is going to image this aperture onto here. But when you make the aperture small enough that it's generating spherical waves, that's when you get the smallest spot size. So the spatial resolution of this Stixum microscope requires spatial coherence. If you fool around, if you double the size of the pinhole, you'll actually get 4 times as much radiation. That could be very nice for your experiment, reduce the counting time or the data taking time by a factor of 4, but your resolution will suffer something like a factor of 2. Okay, so that's the so how does it work then? So then this spot size is produced, and this your sample is raster scanned left and right, up and down in front of the spot size. There's transmission of the radiation through to some, could be just a point detector in the simple version of the Stixum, which is the way it typically works. And so you just get a signal here as the sample is raster scanned, okay? And you then have the absorption properties as a function of position. Often what they do in the Stixum is they want to look at the chemical properties. They not only want to see nanoscale images, and these can be nanoscale images of order 10 nanometers, okay? Recorded here electronically, quick feed out. But in many cases, they're interested in the spectral properties. So they'll actually do a full scan like that, and then they'll change the grading a little bit to change the photon wavelength and photon energy, do the whole thing over again. And they may do that for 100 or hundreds of different photon energies. They'll record this. So now they have the absorption properties as a function of wavelength, and they can look at images with near edge structure and stuff like that. And for instance, a big use of this microscope is for environmental studies, where the binding of atoms, of elements within different molecules changes with the molecule that it's in. And some molecules are very deleterious and others are not, and you can capture all of that. So it's a big use of this microscope. There's one up in Canada, there's one, there are quite a few in Germany and France, etc. So I think I captured that for you.
Professor?
Yeah, please.
You said something about 1 over p plus 1 over q, and that detail went over my head.
Oh, thank you so much for catching me cheating. So I'm guessing that even back in high school physics, which you probably took as a chemistry, right? You had a lens with a focal length, and you drew ray diagrams to show how the light could be focused from one place, or there'd be an arrow, and you'd focus, the arrow would be vertical here and it would be upside down here, and the distance from the lens to the object itself, we'd call the object distance, maybe p. And then the distance to the image itself, we call q. I'm calling q. And the lens equation would be 1 over p plus 1 over q equals 1 over f, where f is the focal length of the lens. Okay. And by the way, I forgot to say it, but I did say the focal length of a zone plate depends on the wavelength. So in the Stixum, if you start doing a chemical analysis work where you're changing the photon energy to look at different absorption edge features throughout your image, then the wavelength is changing, and you have to shift the distance here just a little bit to make up for that change in focal length. Okay, any other comment? So here's an example of holography that was done at Berkeley, which is the synchrotron in Berlin, the Berlin electron synchrotron, blah, blah, blah. And this is an experiment that was done. Here's some of the features. It was using undulator radiation, which would have been back here. They used a 20 micron pinhole, quite a typical size. This is looking at, I think it was an iron, but I don't see where I say it. Oh, magnetic film, but I think it was iron. So they tuned to, I think they tuned to the iron L edge, as I recall. If someone sees it in the diagram, tell me. But anyway, so there's an undulator, there's a pin and a monochromator not shown to get the narrow bandwidth. And they need that anyway for scanning the magnetic absorption edges or scattering, etc. So they have a pinhole, it launches spherical waves. Those spherical waves illuminate a big pattern here. And the pattern has a little tiny pinhole and a big pinhole. And they're this is quite a bit bigger. This little pinhole, like this pinhole, approximately satisfied our relationship for d times theta equals lambda over 2 pi. But you know, for a hard aperture, it's not Gaussian, so the formula changes a little bit. But anyway, this pinhole was chosen to approximately launch spherical waves. Then to do a hologram, there's a little pinhole here. There's a small aperture here, which does tightly satisfy that relationship. So coming out of this pinhole, there are spherical waves. And this other area, this other aperture, rather than be open, it's covered with a material, which, as I said, I think was iron. And so the radiation goes through these two places. This is launching a so-called reference wave, spherical waves, okay? This is modified wavefront, but it was coherently illuminated from behind, but it has an absorption pattern which depends on the magnetic material, and that's what's shown here. So the diameter of this pinhole was something like 1.5 microns. I forget how big this one was, but a lot smaller. In fact, smaller than this one, I think. Okay, and those wave fronts, one that's producing spherical waves and the other one which is not producing spherical waves anymore. They were spherical coming in, but then they went through the magnetic material with some absorption here and there and these so-called worm patterns. And those wave fronts meet on a CCD detector, shown here. And you can see the interference patterns. First of all, you can see what looks like airy patterns. And then you can see interference all over the place. If you were making a really good visible light hologram, you wouldn't see these airy patterns. The reason is it has to do with the areas of these two apertures. Usually in a really high quality hologram, although you want a small pinhole for coherence, you want the light coming through the reference wave to be stronger than the other. Wasn't possible here, but nonetheless, they managed to pull it off. They got very nice interference patterns, and they were able to reconstruct those and back propagate it and produce what the magnetic material looked like. And they compared it with a Stixum at Berkeley. And so they compared the two compared very nicely. And I didn't say it, but this was a joint project between Stanford and Berkeley people. And in fact, Stefan Eisbit, Jan Luning, and Bill Schlatter, the three of them were graduate students at the two universities, at the nearby universities. And these were their thesis advisors, Wolfgang Eberhardt and Joachim Storr, and the magnetics people that provided the magnetics material. But at any rate, we once had, for many years, we had a Stanford Berkeley summer school. And 1 year, we really got into this coherence issue. Both the Berkeley and Stanford students really got into it, as did these three guys. And we've all been close ever since. So Bill Schlatter if we were to go to SLAC for a tour, he would be one of the people we would see. And Eisbit and Luning. Luning is back in Berlin. He was a professor at the University of Paris. And Stefan Eisbit is a professor in Berlin, but he does a lot of experiments in Lund, Sweden. Anyway, it was not only a great experiment, but they got the front cover of Nature for the December 16th issue. So just before Christmas, it came out, and you can believe there was a lot of happy people. And you know how Nature can influence careers, so it did. This is what the front cover looked like. Okay, do I want to show you this? Let's have a show of hands or voices. This is an example of how to make a visible light hologram that demonstrates spatial and temporal coherence. But I could save this for a smaller audience because it's a little time consuming. So all opinions are welcome here. What would we like to do? Should I leave it for the end? Should I leave it for another day? Should I just say a few words and you can read about it if you want?
I think a few words would be good.
Okay.
Yeah, I agree.
Okay, thanks. Okay, so visible light hologram. We're going to use a laser, a good quality, high quality laser with a particular wavelength, let's say in the visible. It comes through. In the visible, we have high quality beam splitters, which means that going through, we have some nice spatial and temporally coherent, very narrow band laser light coming in, some particular wavelength, like 6328 angstroms. Helium neon laser would be a good example. And the light with a beam splitter, light comes through and the wavefront is preserved in transmission and in reflection. Very hard to do in the X-ray region. You may get the forward going wavefront to be okay, but the reflection is just so hard to get a beam splitter flat to X-ray wavelengths. Anyway, there is a beam splitter, splits the beam into a reference arm and a so-called object arm. And these, if you took these split arms, reference and object, and brought them back together again and interfered them, you would get a beautiful sinusoidal interference pattern. But here, we're going to bounce the both of them off a mirror. And one of them is going to bounce off this mirror, bounce off another mirror, and it's still got its beautiful spherical wavefronts, and it's going to illuminate a recording medium. Could be film or CCD. For really high resolution, it would be film. The other arm, the object arm, it's still spherical wavefronts. We open it up with a lens, a negative lens for visible light, and that illuminates the objects. Upon illuminating the objects, the radiation scatters off both of them, and they both, looking from this recording material, looking back, light is not only coming from the reference wave, but it's also coming from the object wave, the two parts of the object wave. And so all of those things interfere here. And now, rather than get a nice sinusoidal interference pattern, which you would have gotten if you had had two nice spherical wavefronts coming in, this one's jumbled. It's completely jumbled. But it has a coherence length of enough waves, maybe thousands of waves of coherence, so that it can still record interference even though the path length differences are not the same. Okay, and so this requires spatial coherence. It requires some temporal coherence so that you can have a lot of depth on the object. To first order, you make the path length from where you split to where you recombine the same. Little differences will appear because of variations in distance, but you have to match this very well. Okay, once you record this, and let's say you develop the film, you then take it over here and you reproduce what was the reference wave before. It now becomes the reconstruction wave, but it's the same thing. And when this wave combines with this complicated wave, if I could use the phrase, this interference pattern, when this illuminating spherical wave scatters or diffracts off this interference pattern, it reproduces the complicated wavefront that was coming from the object, so that if you personally put your head here and look back, you will see the two objects. And this dashed line is showing you that there are places where you, if you look, you could see, if you look at the bottom, you could see the smaller one and the bigger one. But if you look at the top, it's blocking the little one. So this interference pattern, not quite so complicated. That's what allows you to get a true three-dimensional sense, because as you're looking at this thing from this side, if you look through here, you see one thing, but as you move your head down, so you're looking through here, you suddenly see the second object. It appears. So you really have a three-dimensional sense to it. Okay, that was all I had to say. And I just put it there because it's an example of spatial and temporal coherence. And by the way, I have some beautiful holograms I made when I was just trying to learn how this works. One of them is a watch. It was my grandfather's watch, and it has a little lens in front of it. And depending on how you move your head around, the lens is smaller compared to the watch face. And as you put your head up, you can look down at the 6. If you get down, you look up, you can see the 12, and vice versa with left and right. And it's all captured in the hologram so beautifully. You really have to move your head around a lot. For people who hadn't really understood what three-dimensional imaging was, it captures it. Okay, so now some related topics. One is just diffraction. In general, diffraction it's a separate course, electromagnetics course all by itself. Not a simple business. But anyway, a good topic. And so in our chapter 4, there is a section on diffraction. I don't expect you to read it, but I thought I would, unless you have a special interest in it, but I thought I would give you some examples of diffraction and related topics. So in particular, by a diffraction by a circular aperture, a pinhole. We use them so often as optics. So there's a relationship. Here's a diagram. Light is coming in, and it's illuminating and opening in an aperture, and these are the coordinates. And this is a formula for what the electric field would be at some point in the XY plane, okay? And it's a summation in area. It's a summation over all of the electric fields and phase to that point within the field. And so a lot of diffraction theory goes into figuring out what this formula is, and there are varying approximations that you make in obtaining this. But anyway, this is the formula that basically, it's a two-dimensional transform of the electric field in the aperture contributes to the electric field at a certain point. And one of the most famous examples of this is the diffraction pattern of a coherently illuminated pinhole. So this is coherently illuminated pinhole. So this would be like our laser pointer shining on a little pinhole. It's not, because it says coherently illuminated, it's not the light from an undulator or synchrotron, which is incoherent to start with, or at least largely incoherent. And but anyway, if you had spatially coherent, you would find that as a function of position or angle here, k equals 2 pi over lambda, a is the radius of the pinhole, you'd find that as a function of angle, the intensity has this J1 of x over x modulus squared dependence, which is shown graphically here, but this is what it looks like. This is from an actual experiment. This is the so-called Airy pattern, capital A-I-R-Y, named after George Airy. Okay, this is the formula, and the null, the first null. So here's a very, very bright. This is the bright region here. Okay, this is what's shown in the center, and that goes down to a point where there's no intensity here. It's called the null, the first null. Then there's a little more intensity, another ring. This is all axisymmetric. Another ring, another null, another ring, another null. And so here they are. And this is showing quite a few bright central lobe, and then rings, dark rings, light rings, dark rings. okay? And the central ring, this one, the central dark ring, has this formula, so it's called the null angle, which is 1.22 times lambda over d. So d is the diameter, a was the radius, okay? So, oh yeah, and so 84% of the energy is in the central lobe. So this is we use these pinholes a lot. We use them with coherent illumination when we've got it, but we also use them with incoherent radiation as for an undulator at the ALS, okay? So this was the beautiful pattern that you get with a high degree of coherence, spatial coherence. And this is a graph showing what happens when you don't, as a function of some parameter C. This was done by Brian Thompson, a dean at the University of Rochester. And his parameter C would be R d dot theta over lambda 2 pi with a half in front of it. So if we have coherence, this is about 1, and C would be a half, okay? And so here he has dashed lines. So here's C equals a quarter, meaning that the phase space is the product of size and angle, where this is a high degree of coherence, okay? That's his. So here's the nulls that we were looking at before. This is the central lobe, again, as a function of angle. Then there's the first dark null, bright next ring, next null, next ring, next null. What happens though as the size or the phase space product, d and theta, gets to be larger than lambda over 2 pi? So for instance, for a parameter of C equals 1, you start to notice that because of the imperfect spatial coherence, you start losing the dark rings. You can still see a little bit of the nulls, but it's starting to get washed out. And as C gets bigger, like C equals 2, the nulls are just gone. You see little bumps and stuff like that. So this would be a practical example of where spatial coherence on the illumination matters. And how did they do this? Well, this is actually measurements, but what they did was mathematically, they used what's called the Van Sittert-Zernike theorem. So I told you, we took this argument, we got a formula for spatial coherence based on Heisenberg's uncertainty principle. And that was a neat trick because it told us that if we had this little formula, we were going to have a very high degree of coherence. But the Van Sittert-Zernike theorem, which is described here, it can tell you for any distribution here in the source plane, will produce, it tells you what degree of coherence, this mutual coherence function. Remember, this is normalized between 0 and 1. 0, no coherence. Mu means pure coherence. So between the origin and some point P. And what you go through the mathematics, and if anyone were interested, it's also in the book. It's derived, a very geometric derivation, where you look at the intensity that would reach from some point, what intensity or what electric field would reach here, what would it be, and also what's the phase shift, and you add all of those things. And what you find in this theorem is that the degree of mutual coherence, the normalized degree of coherence, is the Fourier transform of the intensity pattern in the aperture. So whatever the shape of the aperture is, whatever the intensity distribution is, you take its Fourier transform and you normalize it to this, leaving out the phase part, okay? You just normalize it to the integration of intensity over the whole area. So remember, intensity is power per unit area, and here you're integrating over all the area. So that would be power here. So, and there's some arbitrary phase here, which depends on this distance z, but it's normalized to unity. It doesn't affect your understanding. So that's the Van Sittert-Zernike theorem. It's really a sophisticated business, and it's there if you want to know. But that was the theory that would predict this perfectly, and then they did measurements, which is what's shown here. And for instance, well, we for instance, using synchrotron radiation, we would have not coherent illumination of a pinhole, which we use in our experiments, but we have incoherently illuminated pinhole, which is shown here. So maybe there's some undulator radiation illuminating some area with a small aperture in the middle, and out comes some radiation. And this theta should actually be over here, but I just showed a certain theta, which was at the null, okay? And if you use the Van Sittert-Zernike theorem, this is what you find for the normalized coherence function as a function of angle. So again, the k is 2 pi over lambda, a is the radius, theta is the angle away from the axis here. And again, you get, now you're not plotting intensity, but you're plotting degree of spatial coherence. So if you're looking at 2 points which are very close, they're very close to the axis, you have a high degree of spatial coherence. As you increase the angle, you go towards where there's a null. So it looks very much like the formula, the results we had before, but this is an incoherent illumination, and this is plotting coherence, not an intensity pattern. Okay, so, maybe I should back up. Yeah, in this one, you were plotting intensity. Okay, this was spatially coherent illumination. You got this airy pattern, and it looks very similar. It has the nulls and everything, not quite the same. Okay, again, Ka theta. So that was coherent illumination, and now we have incoherent illumination. This is what we use at the ALS. The high harmonic people who use the laser illumination, if they illuminate a pinhole, they're in the former case where it was coherent illumination because their Ti sapphire laser would be coherent. So both are used. And these, from this example, I just looked at, okay, what would have a mutual coherence of 0.5? So we had our formula before that we got using the uncertainty principle. It turns out, we'll see in a moment, that guaranteed a coherence, mutual coherence across the area of something close to 0.9. Here I took a different value. I just said, okay, what about, suppose I want to know where does the coherence function drop from 1 on axis for 2 points which are very close to the axis to a case where there's 1 point on axis and the second point is off, hasn't reached the null, but it gets down to a normalized coherence of 0.5, okay? And that comes down to some position here, a little bit over 2. So this Ka theta is a little bit over 2, corresponding to mu equals 0.5. And this, if you play this out to 2 pi over lambda and replace the a by d over 2, etc., this comes out to d dot theta equals about 0.7 times lambda. It's different than the formula we had before, but there's several things going on now. This is not a Gaussian distributed. This is a hard aperture. A couple of other different things. But at any rate, it's giving, this is using the Van Sittert-Zernike theorem, and it's telling us, for instance, from this formula, I looked at an example, an experiment that we did for a wavelength of 2 nanometers, undulator radiation at the ALS, and an angle of 30 microradians. That's how far off axis. To get this degree of coherence, the 0.5, we would use a pinhole here that had a 50 micron diameter, okay? A little bit smaller pinhole, we'd have less radiation, but we could get a higher degree of coherence. So that must be very confusing to swallow. Calculating pinhole radiation patterns with coherent radiation, without. It could be a bit, if you're interested, if it turns out to matter to your thesis, you'll go read the chapters. Otherwise, kind of complicated, but the formulas always look the same. There's just little numerical factors here. Does anyone want to comment on how maddening that is, or anything else?
Professor, sorry,
Yeah.
I had a quick question. So this J1 function.
Yeah,
so
Bessel function.
Oh, okay. It's a Bessel function. So
Yeah, I'm sorry. I should have said it from the beginning. Yeah, because this is a radial problem. It's a circular pinhole, so for sure Bessel functions are going to come in, right?
gotcha. Great. Thank you.
Yeah. This is a kind of summary slide. There's Heisenberg's uncertainty principle is related to Fourier transform pairs. If you just have some switch over, if you just have some oscillation that's 100 cycles long at some frequency, okay, so you have a time axis here and the interval, and if you say, and it's n cycles, and you do a Fourier transform of that, what you'll find is that in frequency space, the spectrum is going to look like this. It's a so-called sinc squared function, the sine of x over x squared, okay? So the longer the larger number of cycles you have, then the more precise your wavelength is, and the less and the narrower the mathematical spread will be because of that. So that's just from a Fourier transform. And we'll use this a number of times in the class. It'll come up when we're looking at undulators, which have something like 100 cycles. They'll have a bandwidth of a relative spectral bandwidth of roughly 1/100, okay? So that's a kind of property. These are creates bandwidth pairs in Fourier transforms. And so I'm just looking at this left part, upper left part here. Fourier transform pairs for signals like that would be the uncertainty in time multiplied by the uncertainty in frequency is greater than 1/2. Heisenberg's uncertainty principle would take and put an H bar here. Uncertainty in time, by the way, this is RMS, and that's why I put RMS measures. Most of what's here is RMS, but when it's not, I'm going to tell you. But anyway, if you took this Fourier transform property and put an H bar here, so this would become uncertainty in energy, then you'd have this. And these were RMS quantities, but if you transform them to full width at half max, which we typically use in the lab, what is the pulse duration of your laser? We would typically say, oh, it's so many femtoseconds, and we would mean full width at half max. And what is the energy width? So we could use RMS quantities, but more typically in the lab, we would do this. So this relationship, just with the H bars and the substitutions, gives you this relationship, which we use all the time when we're working with lasers like the Ti-Sapphire laser, which could have a pulse duration, which would be this, of say 20 femtoseconds or something like, let's say 18 femtoseconds. If this was 18 femtoseconds, then if we divide both sides by 18 femtoseconds, this goes away, the femtoseconds go away, and you'd have 1.8 divided by 18. So the energy width would be 0.1 EV. So that's what we would call bandwidth limited radiation. That's the energy width that you would have for a very short pulse like that, okay? And so you have the same things if you were plotting oscillations in distance, not in time, and then there'd be an uncertainty in K, again, 2 pi over lambda, so 2 pi and delta lambda, and the same relationship. And for the uncertainty principle, which is what's on the right, this thing, we just put our H bar K, H bar on both sides. So we'd get an this would become delta P, momentum, vector momentum for the photons, and this would be H bar over 2. So those are relationships that we will use a lot. High harmonic people use them all the time. And in addition to these, we have the formulas for temporal coherence, which we often call longitudinal coherence, meaning in the direction of propagation. So we estimated this, came up with this formula. And remember that the factor of 2 is a little bit arbitrary, but for instance, it depends on definition, but it also depends on the line shape. So different laser if you look in certain laser books, they'll have this number depending on various things, how close to saturation you were, etc. So this is your the temporal coherence length, propagation direction. This was our spatial coherence, which we got from this relationship. You know, okay, and these are RMS quantities so far. But I find it, as I did up here, working in the laboratory, the relationship, the so-called bandwidth limited relationship for energy and time in terms of full width at half max, also for spatial coherence, I find it equivalent to go from RMS quantities shown there to full width at half max. This means that D and 2 theta are both measured full width at half max. And if you just go through the constants that are involved here, it comes out to 0.44 lambda, which I write as approximately lambda over 2. So those are the relationships that we get out of these coherence considerations, and we'll use them. And remember that I posted on the B-Course site a file that just has a lot of formulas, and it just follows the book. And these will be there in the chapter 4 area. So is there a question or comment? I'm going to change. We're going to lose a minute or two here while I change over to chapter 5 slides. But does anyone have a comment? Okay. Okay. Whoops. Okay, so now we're ready for synchrotron radiation, so we'll get started on that. So we have a little time today, and we'll probably spend 2 more lectures on it after this. So this is a kind of important chapter for quite a few people in the class who are using synchrotrons for one reason or another. This is one of my favorite diagrams for it. Again, I copied this from John Mady. Unfortunately, the late John Mady, but he's the one who invented the free electron laser as a graduate student. Here's our diagram of undulator radiation. We'll go over it again in a moment, and we already have, where there's, it's a periodic magnet structure. So you notice the north and south poles are alternating so that on axis, there's a sinusoidal magnetic field, and it's causing the electron through the V cross B force, the Lorentz force. There's a V, which is this, the velocity of the electron coming through, which is almost the speed of light. And there's a vertical B, which is oscillating. And so the V and the cross with the B leads to an oscillation in and out of the plane. So if there are 100 or n periods, 100 periods, there's going to be 100 cycles of oscillation. And therefore, we expect we're going to get a radiation pattern, for instance, a dipole radiation pattern with an oscillation of 100 cycles. And the question is, well, gee, we've seen earlier that produces dipole radiation, these big lobes that look like a donut. But here we see a narrow forward cone. So that's what we want to explain that, and we want to relate this wavelength to the electron energy coming through, or the Lorentz factor, gamma. How close is it to the speed of light? To the undulated period? 1 period. These are usually centimeters in dimensions, but these wavelengths could be nanometers or angstroms. We've also seen that we can do spatial filtering and aperture filtering, the D and the theta in that formula. And these are some formulas. We will speak briefly about bending magnets, not so much. We'll talk even less about Wiggler radiation, and you have to ask me why, okay? And we'll talk about undulator radiation. And undulator radiation is the more interesting one. It's why all these new machines were built over the last 20 years. And these are the formulas which we're going to come up with for what is the wavelength on axis, how does it depend on the undulated period and the Lorentz factor, okay? And what is the half angle of this radiation? It turns out to be microradians, okay? What's the spectral width? Roughly 1/n, where n is the number of magnet cycles. How much power does it radiate? We're going to derive this formula, and we'll see that for the ALS, the power in this central radiation cone within this bandwidth is, for the ALS, it's typically a watt of power in a bandwidth of, let's say, 1%. At argon, where they have harder X-rays, so gamma is higher, they'll typically have 10 or 20 watts, but similar bandwidth, okay? We'll come back later to the bending magnets and the wigglers. And one thing I'll just comment, this is the more interesting topic, the undulators. It's also something we can explain relatively easy. It turns out that the bending magnet, as simple as it is and how easy it is to use and how many there are at the ALS, calculating this is a bear. This is classic, this is relativistic electrodynamics to get that formula. I'll show you roughly how we get it without doing relativistic electrodynamics, but here we wind up using some things that we already know, even from high school, about relativity, really simple stuff, and we'll get these formulas. This is just to remind me, as I may have said before, with synchrotron radiation, you can basically get to probe any element in the periodic chart, or just about. I mean, hydrogen and helium and maybe lithium have their edges a little bit too low, but the rest of them you can get. Yeah, was there a comment? How are we doing on time? Okay, there are, I would say, at least for our laboratory sources, there are three basic sources. There's bending magnet radiation, where an electron is just going around, and because of some aperture you've set, the electron is going around and it's producing what looks like a little searchlight. We'll understand why it's, and it has an angular width of 1/gamma, where gamma is this Lorentz factor, 1 over the square root of 1 minus v squared over c squared. For the ALS, gamma is going to be a number close to 4,000, okay? So this is going to be milliradians in angular width. And so it's like, if you will, there's like a train going around a circle, and there's a searchlight on the train, and just at the right point, that searchlight flips past your sample, and you get illumination, and it goes on. And actually, there's a time structure here. It's shown as 1 electron, but we'll actually have electrons in bunches, and they'll be separated, and you'll get one of these searchlights flashing by, and then another one flashing by, etc. So that we call bending magnet radiation. And in the sense that we were looking before at Fourier transforms, when we had 100 cycles, we got a narrow bandwidth. What happens if you have only 1 cycle, or in fact, fraction of a cycle? That n equals 1 or n equals 1/2, that has a very broad spectrum. So bending magnet radiation, we expect to have a really broad spectrum, which makes it useful for some people, because they can put their sample in front of the beam, and just by changing the monochromator, they don't have to touch anything else. They could scan a lot of different photon energies, okay? And also there's a lot of bending magnet openings around any ring. At the ALS, there must be 40, something like that. So for people doing PhD thesis, if you can live with the bending magnet, it's easier to get beam time, okay? Another thing is to have a wiggler. It looks like an undulator, but it's only got a few cycles, like 3 or 5 cycles. So it goes like this, and it has a very strong magnetic field. Not so many cycles, but strong magnetic field. So when the electrons are coming through, they really get jerked around. And wigglers produce radiation that's somewhat like the bending magnet, except it's a lot stronger. First of all, because the magnetic field is stronger than the bending magnet field, this can be stronger. Here, if you made the magnet strength stronger, the electrons would crash into the wall. So you're sort of, there is a field which allows the electrons to go around the entire ring without ever hitting the wall. If you try to make it higher than that to get harder X-rays, you'll see the formula in a moment, doesn't work. But if you have a short periodic structure, you can have much stronger magnetic fields. You can get harder X-rays. So this peak on the bending magnet, for the wiggler, it moves out further. Okay, so in the electrical engineering sense, you would call it a frequency shifter. And then there's the undulator, which we were talking about with the diagram. And now you have many oscillations. It's a periodic structure like this one, but now it has 100 oscillations. And the amplitude of oscillations is quite small. So rather than get a big angle, you get a relatively small angle. These were both sort of 1 over gamma, so 1 over 4,000. This is 1 over 4,000 times the square root of n. So if n was 100 cycles, magnet periods, you'd have a 10 times smaller opening angle. Okay? And you wind up producing these very nice spectral peaks, which have a width of 1 over n, so maybe 1% or so. We'll see that you also get harmonics. So we'll call this one n equals 1. We'll see n equals 3, n equals 5. There are even harmonics, but generally they'll be a lot smaller, and we'll explain why. Anyone want to raise a question?
Is there any significance to the dashed line on the start of the Wiggler radiation graph?
Oh yeah, thanks so much. Yeah, with the bending magnet, I didn't have a dashed line because that full spectrum was there. But what happens here in the wiggler, which I'll show you probably in a couple of lectures from now, is that you get spikes like you did with the undulator, but you get so many spikes that it's not really a continuum. It's a really noisy spectrum here, and it's only that they merge at a certain point and start to have the same shape as the bending magnet, so that they smooth out at a certain point. But for the lower photon energies, it's extremely noisy, really spiky. So thanks for the question. Okay, so here's our undulator, and we have a little time. So I think I'm only going to show you another 2 slides after this. So this is just to get our geometry right again, okay? Here's the periodic magnet structure with poles, magnetic fields pointing down and up and down. And these always are in loops, you remember from magnetic circuits. These are going, here they're going this way, okay? Whoops. So there are always these loops. So when on axis between these long magnet structures, on axis the magnetic field is vertical and it's highest at these pole pieces, okay, and minimum in the middle. So we approximate it as being a sinusoidal magnetic field. It's pointing vertically, but it's varying this way. So there's a vertical magnetic field. There's electrons coming in with a velocity almost the speed of light. So the Lorentz force, the V cross B, the V is, as you see, the electron's velocity, and the thumb is the magnetic fields pointing up. And so the Lorentz force is V cross B, it's in and out of the board. And that's why you see oscillations here, which are meant to represent in and out of the board. So if we call the one magnet period lambda sub u, the undulated period, there'll be n periods. So at the ALS, these typically, there are some that are n equals 55, there are some that are 89 periods. With the new upgrade, there are going to be some that are over 200, I think close to 300 periods. Okay, so for instance, if they have 100 oscillations, 100 magnetic periods, then the electron is going to undergo 100 oscillations here, and we can expect it's going to radiate. Okay, the electron is being accelerated in and out of the board, and whenever a charge accelerates, it radiates. And there's this dipole pattern that we understand. The electron feels and radiates. But at any rate, that's giving us a bandwidth of approximately 1 over n. So that's why we have that at the lower part here, that within this radiation cone, the bandwidth is about 1 over n. And the half angle of this radiation cone we're going to find is 1 over gamma. Gamma is this Lorentz factor, which again is like 4,000. So for the ALS, if we had 100 cycles, be 4,000 times 10, it'd be about 10 microradians. So usually we have n as a little bit less, and this asterisk has a meaning we'll come to. It's a small effect, but we'll typically find that these are not 10 microradians, but maybe 20, 30 microradians, okay? And the wavelength on axis, we're going to find, there's a little bit more complicated formula than this, but it's basically the undulated period, which is a few centimeters, let's say 3 centimeters, divided by 2 gamma squared. So there's a big contraction here, and this is what we want to explain in the next lecture. Remember, gamma for the ALS is 4,000. So this is 1.6 times 10 to the 7th times 2. So 3 times 10 to the 7th. So if this was 3 centimeters and we divided it by 3 times 10 to the 7th, we've got 10 to the minus 7 centimeters, so 10 nanometers. So we're going to get really short wavelengths on axis. Of course, photon energies go with that. And the question is, why do we have oscillations which are several centimeters and get wavelengths which are in the nanometer or angstrom region? So here's the question. How is it possible that electrons oscillating as they traverse a periodic magnet structure of several centimeter period do not radiate at similar centimeter wavelengths, but rather they radiate at much shorter EUV and X-ray wavelengths? So we're going to answer that. And how is it that these oscillating electrons do not appear to radiate into very wide sine squared theta dipole radiation pattern, but rather they radiate into a very narrow forward cone of microradians, tens of microradians? So that's our questions. And we're going to start, well, let's make this the last slide. So we saw this before. When an electron is just oscillating in and out of the board, it has no motion in the board. So velocity oscillating, velocity, let's say in the horizontal direction, is much, much less than c. Maybe it's 0. This oscillating electron is producing a dipole radiation form pattern, okay, which looks like a donut. It looks like a donut wrapped around its acceleration direction. And if it were moving, there would be a slight shift in wavelength, which we would know by the Doppler formula. Okay, so if we were over here where this arrow is pointing right at us, or our sample, the observed wavelength would be a little bit shorter because thing is moving towards us with some very low velocity, much less than c. This would be the dipole formula. If, however, while this electron is oscillating in and out of the board, producing its dipole radiation pattern, so as far as the electron knows, it's still producing that same dipole radiation formula. But if it does that while it's moving towards the observer or your sample, if it's moving like this, and the velocity is close to the speed of light, then the dipole pattern it forms, those circular patterns, let's say in this plane, they're moving away at the speed of light, but the electrons are moving towards it at almost the speed of light, and the wave fronts wind up being very close to each other, as shown here. And so a wavelength is peak to peak to peak. That is the wavelength. And because of this relativistic effect, it's taken that dipole radiation pattern and pushed it from the wavelength of the magnet period, let's say, it's pushed it to a very short wavelength, okay? And how much shorter, we'll do the algebra next class. And notice that the period is very short on axis, but if you go off axis and look at radiation going out this way, the wavefronts are separated at a larger angle, okay? So there's an angular dependence, and this is what leads, in the highly relativistic case that we're talking about, it's going to lead to very short wavelengths and very narrow radiation cones. And it's all because of the relativistic nature of the electron. So in the frame of reference moving with the electron, it's still the dipole donut pattern, but it is greatly distorted to wavelength. So for instance, if you look at what radiation goes off at almost 90 degrees, even at the ALS, they do far infrared probing of materials. So far infrared, meaning wavelengths of almost microns, many, let's say hundreds of nanometers. And by the way, the formula, the relativistic Doppler shift formula, which we'll use, is looks very similar to the non-relativistic case, but there's a gamma in here, the Lorentz factor, okay? And so, yeah, and by the way, so for gamma equals 4,000, if you just play this out, if this is a 4,000, what's V over C? You'll see that V over C is so close to 1, it's within 1 part in 10 to the 8th or 1 part in 10 to the 9th. So this pattern gets transformed into this pattern, okay? Okay, I think we'll end it there, and we'll come back on Thursday.
Professor?
Yeah.
I think, so I understand what you just said on the previous slide about going from the dipole radiation pattern to a much shorter wavelength.
Yeah.
But on the previous slide, you had this sign squared as the dipole radiation pattern, and that, I'm not sure where that sign, like why would we expect sign squared?
Oh, when we, part of chapter 2, we looked at an oscillating electron to see what its radiation pattern was. And if it was oscillating up and down, it produced a donut pattern that went in all directions. And one of the analogies was to an FM broadcast station, one of those big towers, or yeah, I guess you call it a tower, near the Bay Bridge. There's a big radio tower there. The electrons are going up and down, and they're radiating at some wavelength for, let's say, AM or FM radio, and it's a dipole pattern. It goes in all directions. So it goes towards San Francisco, Berkeley, San Jose. So that was the dipole pattern we found. And so it's just a characteristic of an oscillating electron. And then the question, I guess I don't know where I put it. Oh, here. So this pattern is what we expect whenever there's an oscillating electron. And so in the frame of reference moving with the electron, if you were there with the electron, this is what you would see, okay? But you're not in the frame moving with the electron. You're in the laboratory frame. And this pattern, mathematically, we'll show it in a moment, but because of these effects that we talked about here, the wavelengths getting shorter and the angles getting smaller, I can't find it. This pattern looks more like this. Okay.
Got it.
Yeah, and if gamma was a small number like 2, we would recognize it as a distortion. But when gamma gets to 4,000, it's more than a distortion. This angle, this was still radiating at pi over 4, and here we're down to microradians.
Got it. That makes sense. Thanks.
Yeah, thanks. Anybody else have a comment?
So this isn't a super relevant question, but what does the radiation pattern behind the electron look like? Is it also deformed in similar matter?
Yeah, so if you look in some, especially older texts, they'll show a little bump on the back here. I mean, there is actually radiation going back at these other angles, but it's going to be microwaves or something like that. So for instance, here, we're piling up here, we're going to get nanometers or angstroms here. Here we're going to get the infrared. There is radiation going backwards. It's part of the dipole formula, but it's at such incredibly long wavelengths. So we'll get a formula a little later, and you could ask yourself, okay, maybe not back exactly at this would be like 90 degrees, almost 90 degrees backwards. What's the period? And you'll find it's there. You can figure it out. So what this diagram shows is here we're only looking at X-rays. So all the other stuff, we're only looking at wavelengths that are within some small bandwidth, which we're taking as 1/n being interesting. Anything longer than that, we're not interested in, and we're not showing it. But if we wanted, there would be radiation going out at all angles. And shown here, it wouldn't be much power. Basically, all the power is in the forward direction now. But there would be radiation out the back, and it would be, I don't even think it would be microwave wavelengths. It's probably radio wavelengths. So good question. Thanks. Anybody else? Okay, so we'll look forward to seeing you next time.
Thank you.
You're welcome. Thanks. Thanks for the questions.